go over. The main definition here is a category. It's going to be something that comes with a class of object for any pair of its objects, morphisms, which we can think of arrows that start from one and point towards another object. For any three object composition, so if I give you and the codomain is equal to something of the other, you can compose them exactly the way that you're used to, and that composition is an associative operation. So if I have three morphisms in a row that I'm going to compose, there's only one morphism that I can make. And everything has an identity that works exactly how you would expect it to. On either side, it does not. Functors, because the category has multiple parts, a map between them has to also have multiple parts. So a functor will have an object part that sends the objects of one category to the objects of the second category, and associated to any pair of objects, a morphism part which sends the morphisms from that object X to the second object Y to the image object in the second category. And it will be done in such a way that identities are preserved and composition. And also, I will never write the OBJ and these things ever again once we left the definition, because I will only ever describe left. It will be assumed that you know which part I'm using when I'm applying either an object or a morphism. And then this didn't show up in my first talk, but did show up last time, and I'm going to be making heavy use of it today, because instead of going and explaining the dual object and writing out the definition and proving shit for it, that's kind of a waste of time that I was trying to emphasize before. Once we already have done it in one direction, we can just make reference to duality, and we know that we have both the opposite concept that we got for small arrows, and that any proofs that we had written carry on to the other. I'm going to be talking about limits today, and obviously the corresponding dual notion will be co-limits, but I've never actually going to write those down, and I'll probably just say them aloud. So, with that, I want to return to some examples of limits that we've already discussed before. I just wasn't calling them limits when we were discussing them. And those objects are products and terminal objects. And the first thing that I want to point out to all of you is that these actually aren't different, products and terminal objects. All a terminal object was a product of an empty collection. Let me write down the definition of product again. I'll just follow it really quickly. We say that X together with a collection of projections is a product of a collection of values. A collection of objects in C. If for all collections of morphisms, so technically I need another object, if for all Y in C and collections of morphisms, that's J going from Y XJ. So, and morphisms, these are also morphisms. There is a unique map that Y X such that the components of F are the guys that we specify. That's not supposed to be that. We project down onto the J, by the J projection, we get the J component. Or J component work. Okay, so this is the definition of product. And now I just want to point out that if this collection is empty, right, then I don't have any of these morphisms. I just have an object. And I'm saying that for any other object, this thing won't exist. There will be none of them. But for any object, there exists a unique morphism to my object. And I won't have to satisfy any of these because I won't have them. But that's precisely the definition of terminal object, right? It is an object in my category such that for all other objects, there's a unique morphism. So a terminal object, or rather a product, a terminal object is a product of an empty collection of objects. So in a sense, I never actually defined multiple things. I only ever defined one thing and then showed you two different cases. Terminal objects are actually products, and products are an example of a type of limit. All limits are going to have one thing in common. They're going to be a collection, or they're going to be an object, the limit object, together with a collection of morphisms that leave that object and go somewhere else, do something else. That's going to be the flavor of every single limit. Even the newer ones, which I'm about to tell you about. Before I do that, I'm going to talk a little bit about monomorphisms again. I brought that up during my first talk, but I want to briefly return to it just to discuss the connection with subobjects, and it will be important when I discuss the next type of limit we're talking about. It's called equalizer. I will get to general limits at the end, but it turns out that if we know about products, we know about equalizers, we know about all limits. So that's the reason for it. Just briefly, anybody remember what a monomorphism is?
Injective.
It is the generalization of an injective.
It would be like
but it's got special properties.
it has a left inverse.
Not quite, that's too strong.
So
It will, if it has a left inverse, it will be a monomorphism. It turns out that it's slightly weaker property. There we go. Yeah.
cancellation. How's that different from left inverse?
It's a monomorphism. Huh?
How's that different from left inverse?
Because you can be left cancellative without being left.
Just write down left cancel. You're writing it. So
That is a monomorphism. If F third G equals F third H implies G, you can cancel. Right? And you could obviously do this if you had a left inverse.
Okay.
But you don't have to be able to have a left inverse to do it.
Okay.
That's the idea of what it means to be monomorphic. And for the case of set, in the category of set, the left invertible functions and the left cancelative functions coincide. They're exactly the same. This can happen in other categories too, but in general, left cancelative is going to be weaker. It's going to be weaker than left.
So in the category of algebras, are they the same still? Groups and category groups.
So in the category of groups, a function is monic if it's injective, and that's it. But it's not necessarily left invertible if it's injective. I think it's going to be left invertible if the normalizer of its image is proper. That's been a long time since I've looked at it. But yeah, not all monomorphisms are left invertible in text. You would, if you think about what you would need, you would essentially need like a way to take the big group down onto the image. That. So what I wanted to mention here, the reason why I wanted to bring up monomorphisms is because another thing that you can think, another way that you can think of a monomorphism is that it is a sub-object of whatever object it's mapping into. So in the case of sets, right, for any subset A of a set F, I will have the associated inclusion. It's essentially just the restriction of the identity to that subset. I just send a different point. And this is a way that when I have only access to categories and things inside of them, so morphisms and composition, I can't talk about the points inside of you and say, oh, that's how I know you're a subset. But I can talk about monomorphism. And so I can say that if there is a monomorphism from an object into X, and typically it will be written with this curly arrow. So if you're seeing this curly arrow, of course someone's telling you that this is a monomorphism. And we will, when we're thinking in terms of categories, we will think of a monomorphism, the object itself, as being a subobject. Clearly, it's really its domain that is the subobject, and the monomorphism is sort of telling you how that thing lays inside of the parent object. But since we don't have any way of getting at elements and categories, this is how we talk about it. The idea is that monomorphisms are in fact topology. And in fact, technically, it's not the monomorphisms themselves, but technically isomorphism classes of them, right? Because I can take the inclusion of a set into the set, and then I can take an isomorphism, a bijection that applies to that subset, and compose it. I would still have an injection, and it would still be defining the exact same subset then. So technically, really a subobject A is really a collection of monomorphisms with the property that for any pair of them, there is going to be a map crossing this triangle to commute, which means that you go this way and this way. And this will be an isomorphism. Now, equalizer. The reason I bring this up is to sort of give you an idea of what an equalizer is. The equalizer is sort of going to be the subset of the domain of a pair of functions that causes them to be equal. And it will be the largest such stuff. So if we're given two, what are sometimes called parallel morphisms in the category. What makes them parallel is that they go to and start from the same object. So if I were to write this up diagram, both doing both going to the same place. An equalizer, remember, all limits are going to be of the same structure. They can be an object, a map, the things that matter. But this thing, equalizer is going to be this, an object, I'll just call it B grade. I have new creativity with both. And then for the objects that are here, X and Y, we'll have maps. And so they're supposed to be chosen so that we have X here and my parallel morphisms. Like I said, it's a subset that makes the two functions equal. So when I compose this function right here, it will be the exact same thing. So if you like, an equalizer is actually giving you an object which is a solution to an equation, right? The equation being f(x) is equal to g of x. When you have access to elements x, you can say, it is the set of all x such that this is satisfied. But when you can't say that anymore, you talk about this thing. And theoretically, I mentioned this other map, phi y. You might be thinking, all right, well, what the hell does he have to do with this? He's actually this map right here. It's kind of boring. He's completely determined by these two maps. And this map, but technically he is also part of the limit object equalizer. You go and look it up on Wikipedia, though, they won't mention that bit because everybody else who knows what the hell an equalizer is knows that it's not important, and they drop it. That's not especially great for pedagogical reasons, though, because then when you go and check the limit, it doesn't seem to coincide with an equalizer anymore, and it might confuse you.
Sorry, so an equalizer is an object in the category paired with every possible mapping into X?
It's going to have, when I write down the definition of limit, you'll see that this is a general procedure. It's the same thing that happened with products. I have a collection of objects here, and in this case, X and Y are my objects. In the case of products, I have a map from X to every single one of these guys. In the case of equalizer, I have a map from my equalizer the two objects.
So the equalizer is E phi x and phi y, right?
Yes.
And this is happening for every f and g.
This is just for one pair. This is just F and G are a
For
fixed pair.
Okay,
The equalizer E is relative to F and G.
okay. So yeah, then E also explicitly depends on f and g.
Yeah.
Okay, sure. This is a sophisticated definition.
It is a,
Do you have like an example in a particular category of where an
well, technically any kernel
any kernel is an equalizer?
is the equalizer of your morphism in the zero morphism. I mean, go ahead and write it.
Yeah, could you please? I always compare it to groups. I don't know why. Maybe that's bad.
Groups is really like a really good place to test out all these things. And groups is also a great place to use category theory to cut down on the amount of work. Okay, so we can embed, or we can include the kernel into the domain of the morphism, and we have that morphism and zero morphism.
Oh, they give us the same. Yeah, sure. Cool.
So, and it's the largest one.
Yeah.
Universal property is the largest. So, yeah, I didn't even write down the universal thing. So, an equalizer does this, and for all its prime is this. Is such that same sort of thing. So F so it's another thing that could potentially be the equalizer. It's another subset on which these things are equal. Well, what did I say was true about the kernel? It's not just any subset that causes that advantage, right? It's the largest one. So there should be a way to map the smaller one.
Wait, so E being as large as possible is baked into the definition equalizer?
Well, it is baked into the definition of equalizer by the fact that it has the universal problem. The way that you would say it is that it's terminal in the category of cones over this diagram. I'll give you what all that means. But that essentially means that no matter what, if this guy is another candidate equalizer, we call it cone.
Yeah.
He's got to have a map to my first one. There's this. The unique Q going from E prime to D such that and it's got to make their morphisms end up working out. So here we'll have phi x goes with U is equal to phi prime x. U. So this is the universal property that it not only satisfies this, but if something else does, then I've got my unique map into it, which is say it's saying that this guy is the biggest. Okay. And so I had brought up monomorphisms and subobjects a second ago, and I keep using the words and this is a subobject. It turns out that all equalizers are monomorphisms. And when I refer to the equalizer, I'm referring specifically to this part. That part is not one. But this is the equalizer itself into the domain. Boom. So I'm going to go ahead and choose that. I'm about to use this, unfortunately. On. Right. Well, so this Same setup as before. Be an equalizer. Equalize. That's our assumption. And we want to show that code monomorphism. A monomorphism is its left canceling. So I want to deal with this. We want to somehow show that H and K are equal. Well, if this fellow equalizes F and G, then this also has to equalize F and G, right? Just by simple composition. If I compose F on the left of this guy equals G composed with it. This is an equalizer. This is equal to G composed. Yes, this max, which I will call the, it doesn't matter which of them I use. H. Okay, so this is just by replacing this part, which I know is equal. But that then tells me, obviously, that following that, so whatever the hell domain of H is,
That's supposed to be K for the second.
no, it's also H. Yeah, you can use either representation of the same. So, right, if I had written this composed with K, it wouldn't have done anything. But anyway, so this H.
Wait,
This is a triple, having the property.
sorry, I zoned out, I guess. Where did H and K from? The max correspond to equal.
Some morphisms H and K such that this is working out because I'm trying to show that it's a monomorphism. So I have to start by assuming this.
Are they the monomorphisms corresponding to E prime?
These guys?
Yeah, H and K.
No, they're just arbitrary morphisms. I
Okay.
just grabbed H and K and I slapped phi x on their left side, and I want to show that this being equal causes H and K to be equal because that would mean phi x is left hand.
Mhm.
But what we've seen so far is that this fellow is also going to be a cone to that same diagram. He satisfies this exact same property, just like we grabbed the second time. And what that means is that there has to be a unique, there exists a unique U. No. When you equalize with E, such that I get to take, so if we go and just write down precisely, yeah, I already raised the great. But if we had gotten it, it would have been this composed with U. Is this going to be, this would be equal to the prime version of X here. But if my prime version of X is this right here, it's also equal to so now H is equal to K by the uniqueness of U. U is the unique morphism that causes that you can compose with this guy to equal this thing, but I can also compose H and K with it equal that. That's the case. Uniqueness of U and immediately implies that H and K. All equalizers are monomorphic. Very, very technically, everyone is a subobject corresponding to the largest subobject making a pair of functions paromorphism. Now, it's worth mentioning, every equalizer is a monomorphism, but not every monomorphism is an equalizer. But yeah, it's not necessarily the case that every single monomorphism. However, there are categories where that is the case. So it can be true. We call those categories regular. And if a monomorphism happens to be an equalizer, we will usually call that a regular. Regular. Okay. Showing up in mathematics to mean something else.
Regular is like so overused.
It's used for
Pretty regular.
Pretty regular. What is it? You were telling me the technical of the axioms of topology, how they seem more suspicious as you add more conditions.
right. So now we know about product. Equalizer, absolutely. So once I had the hypothesis for the monomorphism, I just erased it. But yeah, I had these two things equal. Well, now because this guy equalizes F and G, this map that I get by composing, even with A or with K, also has to equalize F and G. As a result, the domain of these maps, together with this map that I got by composing, and then by composing again with either F or G, it has to satisfy exactly this criteria right here. So that's how, and it's not another equalizer object. It's another cone to this diagram. I'll finally write down the definition of cone so that we can stop using that for the property. Now,
Wait,
yes.
so sorry. So here in your definition of equalizers, do you have some sort of uniqueness property?
I
used-
erased it already.
You
Yeah,
erased it, but you had it there, right?
Yes.
And that's what lets you conclude that. Yeah, okay.
And like Jonathan pointed out last time, it is this uniqueness property that's always going to be responsible for the unique up to isomorphism. All of these, if I hadn't included that there exists a unique morphism such that all this composition stuff works out, I wouldn't be able to show that there is only one object up to isomorphism. It's very important that we include that. I just had to erase it for a second. So it turns out that with products and equalizers, we have enough to not only, well, we could have talked about general limits whenever we wanted to, like that's theoretical, but we actually have some tools to be able to prove that these things exist. Because when I write down what they look like, they're going to be very, very general. There's lots of different shaped diagrams that turn out can lead to lots of different types of limits. And that's precisely what equalizers and products actually were. They were limits that corresponded to diagrams of different shapes. Let me start with diagrams, actually. Diagrams. This is going to be a really short definition. The diagram. So for whatever reason, in category theory, we sometimes distinguish between the image of a functor and the functor itself, even though we're really talking about the same thing. And that's sort of what's going on right now. We will call the functor itself a diagram, even though generally when you think diagram, you're actually referring to the thing that you get by taking the image of that functor in another category. We're going to end up using this functor to construct our limits. But for whatever reason, throughout category theory, people interchange between calling them functors and diagrams depending on whether or not they're doing this. I can't explain it. I didn't make the rules. I'm sorry. So this is the diagram. Wait, diagram. This is a slightly longer definition, but it will explain the origin of the form of all these various limits, how they're objects together with morphisms from that object to other things. How does that come? Diagram. X. F. J. J, E, and J. That same J. This is a cone. F. So if the following is true, so if for all f in my what's called the index category. So here j, little j prime. We have the following. So f, this function right here, acting on this fellow right here. So this morphism right here goes from x to, I should probably actually have mentioned. X to s. Not just morphisms over the index category, but specifically for every object in the index category, we're mapping to the image of that object under our functor. And now, this fellow right here, he maps from j prime, so I want to compose fellow that goes into j, and that will equal fellow that goes into. So this is the idea behind it. It's going to be an object to collection of, and a collection of morphisms to the image object of my diagram. And for every relationship between the objects in my index category, for all the morphisms between my index objects, I expect the morphisms of my cone to preserve them somehow, to satisfy this. This is precisely what's being done with an equalizer. So let's see if we can unpack how this guy down here is precisely a cone to a diagram of this shape. It consists of two objects and two morphisms.
So in your picture, so F is a functor, right? From category J to C. J is your index category, right?
Index category.
J is what?
A J is just another category,
Oh,
literally.
But it's like a placeholder.
Yeah, we consider it to be the index.
Yeah.
Just like when you index a set over another set. The index set is also a set, theoretically, but you're using this. So here, this is a cone to this diagram, because as you can see, these are the two images of my object, 1 and 2 right here. I have my morphisms, this one to this one, this one to this one. And lo and behold, when I compose with this guy with F, I end up getting Y, because of the way that this thing is defined. Kind of boring with how it works out that way, but it is in fact a cone. So that is the first step in defining what a limit is to a diagram. We have this what are called, well, technically I haven't showed you what the morphisms are, but right now we have a category, the beginning of a category of cones. Here are the objects. Now let me tell you about what their morphisms. If and Y for both cones is F. We say that I'm using var phi for too many things. I'm sorry. We use a map theta. It goes from, or rather, we say a map theta that goes from X to Y to the cone morphism. If for every J, we have the following. So not just a morphism from the object into the other object, he's also observed all of the important morphisms. Let's take a cone morphism, and it turns out the composition of these guys. So the cone morphism. And so now finally, I can say the short sentence limits our terminal objects in the category of cones to a diagram. We all know what it means now. Bam, we're done. No, okay, I'll explain all of that a little bit further. That is what a limit is. Now that we have constructed the category of cones to F, a limit is just going to be a terminal object, meaning for any other cone, we'll have a unique morphism into it. So something that is unique, a unique one of these theta that causes these compositions to work out. And I'll go coincided with all the shit that we've said already. So, is a limit that it is a terminal object in the category of cones. In other words, it is another cone. There is a unique morphism from Y to X. It's terminal, so everything landed.
So, sorry, Bryce. I'm still hung up on this definition of cone. So what are the morphisms in the index category look like?
I have no idea what they look like.
You have no idea.
There's morphisms in a category. There's arrows that point from one object to another object. And nothing else.
So could you always define, how about this? Just a category of like, so the objects in this category are just like the natural numbers. The morphisms are just permutations of, say, I getting sent to J. Would that form a index category?
I get this thing.
Yeah. So for example, I give you like a morphism from like, I'm having a hard time visualizing the index category. Could you give an example?
Anything could be an index category. So for instance, when we were talking about products, the index category consisted of discrete objects. The only morphisms were the identities to them, but no morphisms connected them. So all of our projections.
So index category can have zero morphisms.
Absolutely, besides the identities.
Yeah.
But like,
well, it has zero morphisms between different objects, then this thing back previously holds, right? So you
this last statement, yeah.
So then actually
That's true.
in that kind of index category, then almost everything's a cone, right?
Any object together with morphisms down to each of the factors is a cone. Absolutely, yeah. It's really easy to be a cone in a case where there is no relationships between the objects. And as you pointed out, the more relationships there are between objects in the index category J, the sort of smaller the limit is going to be. It's going to be losing points. So this is another cone. There's this unique U from Y to X, and it'll be a cone morphism. So it'll name.
No, I wanted to go kind of backwards. I want to construct a cone that gives me just sequence of numbers. That's why I was trying to.
A cone that gives you a sequence.
Yeah. But I don't think it's maybe an extra sense.
Talk to me about it.
Yeah.
Okay, so and this is. So this is exactly the setup that we had for products and equalizers. I have it all erased, obviously, but when we had the case of an equalizer, I gave the definition of a cone, and then I just said, and the cone that's special, the one that actually corresponds to the equalizer, is the one that has this unique morphism from a other guy into it. because it's bigger than all the other ones. So hence into terminal object. Okay. So now that we've got this incredibly general setup, right? These very specific objects, they cause all of these relations to hold with their special morphisms. You might ask yourself, how would we ever construct one of these things? This seems like really crazy complicated. And it turns out that it's never any more complicated than taking products and equalizing. Okay. So, and to illustrate that, I'm going to say about 20 minutes and go through with an example. So I'm going to just take an arbitrary limit in set to just show you how we actually go about constructing this. And then once we've done that, how we go from set the category to arbitrary category, so we want to prove the limit existence theorem. It's really simple. It's really easy. So I'll get rid of all of this for just a second. Give us a diagram in the set. We will explicitly go and construct every piece. Okay. And so if we just recall our definition of limit that I wrote as part of, we already know that the object should, or rather the thing that we're looking for, should be some sort of object. Some sort of object, together with morphisms that go down to every single one of these guys. And we could, for just being really, really, really naive, we could just start by saying, oh, why not just the product of all of the images of this guy? We could take products from J and J, all of these Fj. And the reason to bring him up is because very clearly for this guy, I can come up with morphisms that go down to the individual factors. That would be nice and simple. No, we could call that little FL if I wanted to. That would be nice. The only problem is because I have morphisms in J, right? This only works 100% of the time for discrete categories. As soon as I have 8 morphisms in J, this set of morphisms that I write down isn't necessarily going to preserve all compositions. My key points, J tuples. Okay. This is a set now. So I can actually write down these points and talk about these points. Nothing weird about that. This is a J tuple, which has the property that, well, there might be a, you're going to go to this one, I'll just use, there might be morphisms out there that cause something like this to fail. And nothing in our construction of the thing take the product over the image object in order to deal with that. Why do we deal with that? Well, it turns out by doing the only other thing that I talked about this entire time. We've taken products and subsets. We've taken a product already. The only tool we have left to us is a subset. So the question is there a subset of this guy that I can define such that this is true? And the answer is yes, right? Check it out. Define as subset of this product. This is going to feel really cheap, but it's exactly, there's nothing cheap about it. Find this to be all of our J tuples in the product. such that this is actually true for all L and L prime. And all L prime and L. You might think to yourself, wait, we didn't do anything. We just said, yeah, we just have, yeah, but we can totally define sets that way. There's nothing, the set all X that does a thing. You have the ability to do that. CFC gives you the power to define that set. So we will simply just do that. And that tells us exactly what a limit is in set. And sort of heuristically what it is everywhere else. A limit is a subset of a product. That's it. This makes it look really crazy, like there's some really weird arcane construction procedure involved. But from the definitions that we've got here, it's pretty easy to see that it's nothing more complicated than taking a product and then taking the appropriate subset of it. Now, how do we go ahead and express this in categorical language and on set theorem? Well, I mentioned before, equalizing your subset. We already know products in general categories. That part of the procedure, if we can get to here, this is fine. It's just going to this part, the subset that causes this to happen. Well, as long as I can come up with a pair of parallel morphisms from this guy to some other guy, whose equalizer is this guy, well, then we're done. So we'll write them down in component form at least. And we will all agree that's exactly what they'll do because it's in manifest when I write it down. And you understand limits and categories. Right? It took you guys a lot less time than it took me. Okay. Okay. So this is where my morphisms are going to start and where they're going to end. And then each one of their components, the various f, that's all I have to tell you, because once I told you the components of a product function, I can uniquely determine the components.
So there's two maps, S and T, or is it such that?
This is S and T, these are maps.
Okay.
But yeah, so if I can give you the components of these maps, and this thing is indexed over S, but I can give you, so for every F, I can give you the components of these maps, and I will specify everything that I need to specify. So for a given F, the component of S that I want is F, and he will go from, he goes to, okay. Great. Oh, right, I'm using, I should have used a different name for all of these symbols. That'll just have to be weird. This thing will be the component of S, and then F.
Wait, so I'm trying to understand this is so that I got so hung up on cones that I missed definition of limit.
Sure.
Yeah.
This, that.
So what you're suggesting is instead of using definition and limit, we can compute the product of these FJs and then set the equalizer to be
Equalize literally by saying, oh, I think this equation to work out.
yeah. Wait, so what's the equalizer? So equalizer is three things. It's our set and it's two other maps.
Two other morphisms.
What are the other?
Often you'll only see the morphism going to the domain given because the morphism to the codomain is always determined.
Could you write out the morphisms for me real quick?
Sure. So
sorry.
You'll have your E, you'll have your map phi,
yeah,
X, parallel morphism. And I have written it here, it's hidden, And the reason he's hidden is because he's fully determined by all the other guys here.
Mhm.
But E isn't just E phi. We've also E another map. I have to go to all of the objects in the diagram, right? Not just X, not just the domain. But the way that I make this guy is just by composing F with other. Once I know this guy, these guys are already there. I already know what he is. And there's only one thing he could be.
Yeah, so E here is S, right?
E here is, yes.
Yes.
Here is S.
So what's phi here?
Phi here is going to be the map, the restriction for these things.
Okay.
So you just take S, and then these FL that I define, you simply restrict them to that subset.
Okay.
And it's literally because like they couldn't do anything else. I kind of did the dumb thing and just it was the only thing that could work. And before you've seen it, all of this sounds really, really complicated. Once you have seen the construction of it, it's like, ah, subset. But there are lots of possible ways that you can construct different types of limits because there are lots of different shapes of categories. So we talked about products. Those are when we have J is of shape discrete. There are no connections between any objects. But there are other types of shape. Parallel morphisms are a shape of diagram, a shape of category. And we have already found that the limits corresponding to him are equalizers. There is limits corresponding to partially ordered sets or categories which are partially ordered sets. We call these direct limits or inverse limits. It flips between co-limit and limit, and it's not the one you expect it to be. So
yeah.
I can never remember it, and I always just look it up. Okay, well, so we've seen limits, and this is, by the way, this allows me to conclude, since we can see here now that all a limit is an equalizer that I construct from these products. As long as I can construct equalizers and I can construct products, I can construct limits. Bam. So if you're ever in a category and you want to know if it's complete, you can construct any limit you want. You don't need to go off and show that for this thing, which would be awful. You can just do it for products and then do it for equalizers, and you're done. And this also works at varying levels of finiteness / cardinality. So if you want to show that all finite limits exist, meaning the categories here are finite, there are finitely many objects, finitely many morphisms between them, you only need to show that you have finite products and equalizers. All finite limits will only ever end up taking a finite product in this step. Same will be true if you want to talk about small limits. That's when all of the categories here are small, meaning that their object set is a set.
So you used the category theory borrows two words from points of topology, the words limit and complete.
It does, and they're not used the way they should be.
Yeah, okay, that's what I wanted to ask.
Limit does not mean limit like in calculus at all. It's a terrible name. It should not have been named that. I can't do anything about it, so I'm sorry. It gets even worse though, because functors that preserve limits, that's what they're called. What do you think they get called? Continuous functors. Oh God, that gives this impression that there's some sort of structure, like shape of the category that this is preserving.
No continuity at all. No smooth structure.
Sense, I guess, but not like that. No.
Okay.
So, yeah, terrible. There's a whole bunch of things that shouldn't be named. Any questions? No? Okay, well then I'm going to start that was mostly what I wanted to talk about. I think the only other thing to mention is, because I've done everything on the limit side of this discussion.
By the way, you have like a 5-6 minutes before now seminar starts.
Yeah.
But keep going. They start late anyway, so it's fine.
Yeah, so obviously dual to this entire discussion was the discussion of co-limits, right? Take a word in category theory, add co to it, you're doing new category theory. And the only thing that would have happened throughout all of this is that we would have reversed the arrows. So as I showed you when we were talking about co-products, it is just products with inclusions maps up to the big object, away from the factors, instead of mapped down from the big object to the factors. And the same is true for co-limits versus limits. I just flipped the order of compositions, changed the direction of arrows, all the exact same things working out. We have objects called co-equalizers in addition to co-products. And you can construct the general co-limit by taking co-products and then co-equalizers of those co-products. What the hell is a co-equalizer? Is it like a sub-object of something? No, we turned around. The dual notion to a sub-object is a quotient. It's like a quotient of a disjoint unit. You need a whole bunch of stuff together, and then you said some of the points are actually the same. And that's what you did when you did it. There we go. Any other questions? Or is everybody mostly confused? Good. All right. Yeah, no, by the way, all of this stuff is very difficult to understand.
Good that we're confused or good is that?
It took
No
me
questions.
lots of times of like reintroducing myself to material before it really stuck.
Yeah, I think this is maybe my second time. The first time I seriously tried to digest limit and I did not. I felt horribly.
It's a really easy thing to get discouraged
Yeah,
at when you're doing it. And so don't feel bad about that.
it takes multiple submersions.
Exactly. Break it up into manageable pieces rather than trying to go and lift 300 pounds per person. Right? That's how you're doing it. And thank you all for showing up. I hope that you're able to find some use for category theory in either your studies or your research. I want to save you time.
Are you suggesting Dima hurt himself when he was trying to learn category theory?
I'm not going to say yes. Next time I talk, I will try to bring some of my research up to you guys. Why the hell I get a PhD position?
Okay, so that's the end of the talk. Next speaker.